Alright, we're going to continue our discussion about GD&T inspection. I left off the last video a little bit early. There was one more point I wanted to make about form error, in particular cylindricity, and it had to do with the flange part. When you take a look at the print, there's the ID, what is that, 0.317 plus or minus 1. It has a cylindricity requirement of 2 thousandths, which is essentially plus or minus 1. It's a little redundant. But how would you inspect that? I neglected to cover that before the last video, and it's not so straightforward, I think. The tolerance is so tight, you can't really use a caliper, can't use a telescope gauge, a small hole gauge. You could maybe use a 3-point hole mic if you could get one really small. But the best tool for the job is the pin gauge, as I've said. So how you would do this is you would grab the go size 316 and you would put it in, and you would grab the no go size a 319, and it wouldn't go. And as long as that passed, you're verifying your go size goes and your no go doesn't go. Well, that's a 2 thousandths difference, right? The way this is toleranced. So that satisfies the cylindricity requirement. But let's say you didn't have that plus or minus 1. Let's just say you had a cylindricity requirement. And what you could do is you could grab all your pin gauges and you would stick the pins in one after the other until you found the size that goes all the way through, and then you find the next size stops. Maybe it stops about halfway, doesn't quite poke through. So you have your go size. Our go size is 316.5. And I don't have the whole set here, unfortunately, but I can try to simulate what would happen. You stick your 317 in, and it goes part of the way, and it stops that far. And then you stick your 318 in, and it doesn't go quite as far. It's much further down in the hole. And your 319 is much further down in the hole, but it does start. So if 319 starts and 316.5 goes all the way through, what does that tell you? That tells you have a taper issue. And that's a cylindricity issue as well as a taper issue. So 316.5 to 319 is 2.5 thousandths. So that's just barely out of our spec, our 2 thousandths spec. And that's a very easy way to do it with internal diameters, pin gauges. Just keep checking them in. And I got a very good part here. The one pin goes, and the no-go doesn't even start at all. So I only have the one size that goes in smoothly. The next size up doesn't go at all. So I have very little form error on this part. But that's how you would do it on other parts that may have larger form error. So we're going to keep rolling. We're going to keep doing. We're going to do runout, and we can work with this part going forward. Actually, we'll do this one second. We'll look at the runout of the shaft. That'll be a little easier to start with. So let's take a look at our print. We'll do the total runout, which is the double arrow of the 508. We did the cylindricity check of this earlier. And I do want to remind you guys, I have this drop indicator here for a reason. Some of these checks are going to be a little bit easier with a drop gauge. So I'm going to demonstrate just this one, maybe another one coming up. But I'll try to demonstrate how the drop gauge can make things a little bit easier. So I am only stacking these on top of each other so you can get a nice shot of the indicator. And let's see, how am I gonna to push this a little bit off center. All right. So what I'm going to do, we take a look at our symbol. It's total runout to datum A. So we need to know datum A is this paired diameter here. So I'm going to be registering my V blocks on those diameters. And I'm going to set up my V blocks so that I can get to my indicator. And all right. Apply a little bit of pressure when you're working with a matched pair straight down so that you can center them and straighten them, I should say. And check that your indicator is getting the top, and we'll set 0. Yeah, you can see it. We'll set 0, and now we'll begin to rotate the part. This is what a runout check is. You're going to be rotating this part 360 degrees, and you're going to be looking for how much that indicator moves. And that indicator has moved 1,000th total. I've seen about plus or minus a half. Our tolerance is 5, so we're well within spec. We're going to move to another point further out and rotate again. Now our resting 0 has shifted off a little bit. It's no longer resting on 0, so that's a little bit of error. It's now resting at 3, and it's going up to about half. So overall, my total indicator that I've seen, I saw a minus half when I zeroed it, and now I'm seeing about plus 3.5. So my total indicator is 4, and my tolerance is 5. So even though there's a lot of chatter on this, the runout is passing the requirement. Now earlier on we looked at the size and it was failing the size requirement. It was passing the cylindricity requirement. So everything about this is fine except it's too big. Now I want to point out, the first place I checked, I zeroed it over here. And I didn't re-zero it when I moved it to farther to the tip, because that would actually eliminate some error. Like I said, if there's a taper, if it's tapering downward, I want to know that in my runout. If it's bent, and I re-zero it when I move, well, you're hiding some of that error. So taper, again, it can be straight, but that's a runout issue as well, unless there's supposed to be a taper there, right? But there's not, so it should show up as runout. Now we're going to move on to the next one. The next one was just the single runout. It's a two-dimensional runout. It's not the total. So once again, we're going to go 2.5 from our end and just do that one spot. I'm going to use the drop indicator again so that you guys can see, it can be a fairly useful tool in many of these applications. So I've got it on my dot there. I'm going to zero this out, and I'm going to rotate it around, and it's dead on. It's barely moving, 1 or 2 tenths, maybe a half now. Almost no error. And we were allowed 3. So one of the applications, why would somebody choose total runout or just runout, right? Total runout or runout. Most of the times you probably should choose total runout because you care about the entire diameter. But there are some applications, like a step shaft, where there's an assembly feature and you have a very, very long diameter, but the critical portion of that diameter is only in one location. So they want you to check that location where there's some sort of assembly feature, a bearing, a support, whatever it could be. So maybe a gear gets attached. So that's one reason. And another reason, sometimes when cross sections get really, really small, which we're going to see on the next part, putting total doesn't really help you when it's such a thin cross section to begin with anyway. That might be another place where you just see a regular runout symbol. So we're going to set aside our drop indicator, and like I said, it's good for many applications. I like resting V blocks, paired V blocks, and using an indicator, but we're going to move on to the back to the test indicator. It's going to be a little bit easier to work with. And we're going to move on to the flange. We're going to do a couple of runout checks on the flange. So that's PM04. And let's look at our datums. So let's find our datum. Our datum is the ID. It's the internal diameter. So what I'm going to do is I'm going to clamp a pin down and rest my part on that datum. That way I'm simulating what the print wants, and I'm getting a very stable setup. So clamp you down. Oh, there we go. It's not rocking. Check for stability. And now let's look at what runouts we're talking about. First one I think I'll measure is the outside diameter 627, running out 3/1000 to B. So I've got my pin gauge on datum B, my part rests on my pin gauge. So I'm pretty much set up for a direct measurement. All right, I'll zero you over here. And I'm sweeping, trying to find the high point, just like we always do with indicators. And now I'm ready to just rotate this around. You're going to see it jump when it falls into the hole, but otherwise it's pretty good. And this is a total runout, so I'm going to get another section. And it's really your choice whether you want to slide around the part in the V block or you want to slide around the height gauge. That's up to you. I interchange, but otherwise we're looking great. No error at all. We have 3/1000 relative to B, and we have no error. Next up, we'll do the single arrow runout. This is just called runout. 5/1000 relative to datum B. Datum B is our through hole. So all I've got to do is raise up my indicator, and again, sweep and find zero. Find the high point, set zero, and spin. And I gotta be very careful. So I'm gonna weight this down a little bit. You'll probably see me do this in some of the other videos. And I'm spinning around, and I'm seeing almost no error. So this part was made pretty good precision on some sort of lathe, I would assume. Very little indicator movement, so we're looking good there. If you want to see, you know what, I definitely should show you what a test indicator looks like on the match pair. So let's do the runout check on the end again, because most of the time I think what you're going to do is use a test indicator and V blocks. So let's do this one again just so you can see. This one's a 5/1000 total runout. So I'm having a little trouble zeroing it. All right, and then I'm seeing about, see it jumps because of I slid it maybe. You see about 1,000th at that point. I'm not going to re-zero it. Oh, see now my zero is much further off from where I started. I'm getting all the way to like -4.5, -4. Yeah, so again about -4, -4.5. But again, fairly easy. Identify your datums. Get them rested in the V block. Or if it's an internal datum and you can use a pin, do that. Let's do, let's modify our print a little bit. As we did in the surface plate videos. Let's talk about, there's a datum B on the internal, and we're checking our diameter relative to datum B. But what happens if you flip that? What if the diameter on the outside is the datum and the internal diameter is what you want to check to? Let's just flip the tolerance and the diameter, the tolerance and the datum, and show you what that would look like, because that will happen a lot as well. So my datum will say is on the outside, and we will just try to sneak the indicator onto the inside to measure the runout that way. And what I'm going to have to do is sweep, find the low point. You see where that inflection point changes. And now I have to very carefully find the runout. So now I've got my indicator. On the inside, and my datum, we've said for this sake of this argument, is on the outside. And that's how you would do a runout check from an outside to an inside. You don't use the pin because you need to get your indicator in there. There's some applications where you can stick a pin in, and with the datum on the outside and the pin on the inside, what you can do is sweep the location and then rotate the whole physical fixture 90 degrees, pin and all, and check the next location. And make sure the pin isn't sliding around loose in there. Usually when you get the tightest pin in there, there's enough friction to hold it in place. And if there's a problem, you'll still see it. I've done that a few times. Sometimes it's the best way to do it, especially if you have a really rough surface. You'll hide some of that noise. So let's continue on. I think we've covered runout fairly well. We'll take a look at the next set of symbols. All right, location. We're going to talk about not only true position, but concentricity and symmetry at the same time. And if you noticed on some of the earlier screens earlier in the video, all of these have had some sort of asterisk on them. We'll talk about position first, which is that first highlighted here first. And the asterisk with this one, oops, there it is. Position replaces the rectangular tolerance zone with a circular one. And as I mentioned earlier on, I showed you a graphic of two cylinders representing the tolerance zone. And I said, well, you don't actually have two cylinder tolerance zones. You just have one maximum. So I'll show you that in a second. When you do measure true position, it requires you to find the size and the center point of the hole. So it's no different in many ways, whether true position is a requirement or not. You have to find the size of the hole, and you have to find the location in X and Y. But with true position, it's absolutely required because you're going to be doing a calculation to verify you're within the spec of the true position. So the metrology is the same. I have nothing new to show you. Use calipers, use a height gauge and a pin, use whatever you like. Most applications for true position are for holes, but true position can also position square features as well, like slots. So with that, it's the same thing. You try to find the center of the slot by measuring the slot size and the slot center, just like a hole. And if you'll notice, this is the first symbol we've really come across in this video series right here. It has multiple datums. It has A, B, and C. For the most part, we've looked at cylindricity with, no datums. We've looked at runout that has a datum to one, maybe one axial datum, one diameter. But position typically has 2 or 3 datums. So let's take a look. Let's just take a look at this symbol. This is a simplification, fairly common way of dimensioning true position in 2 datums. And this is a modification of the angle block, just getting rid of the datum A requirement and just simplifying the explanation. So we have datum B on the bottom, we have datum C on the side, and then we have our whole pattern relative to datum B and datum C. And we have a true position 14. So what that actually looks like is a ring. A ring with a diameter of 14 and a radius of 7 thousandths. Now this square box, this box represents what your tolerance zone used to be before you added the true position requirement. So you've added a requirement, but your tolerance zone has grown from a square box to a circle with the square box inside of it on all 4 corners. And this is really great, right? You get more tolerance. And, this goes into our discussion about engineering, and also our discussion about, this is for reference only. This square box doesn't exist anymore for you. It's a nice reference to see what happened to the tolerance zone, but you forget about that. You only focus on where your measurement dot, where your center point of your hole. This is not a hole, right? This is the tolerance zone for the center of the hole. The outside of the hole, the edges of the hole are much farther away. The actual edges of the hole are way off on the outside. This is where the center point region needs to lie. So you forget about the square. It's just there for illustration. And then your engineer hopefully gives you a circle that is larger than the square. So why 14? It's an unusual number. Why not round up to 15? Why not 10? And actually, when you take a look at blueprints and you take a look at title blocks, go ahead and look at a few blueprints from different companies if you can. A lot of people are using plus or minus 5 thousandths as a standard tolerance. And so what happens when your standard tolerance is plus or minus 5, that's how big this square is, minus 5, plus 5 in x, minus 5, plus 5 in y. Well, when you try to make, the diagonal corner here, your corner ends up being 7 thousandths. Actually, forget that. Let's say our corner is from here to here, basically the diagonal of the square. Well, when your square sides are both 10 thousandths long, your 90-degree triangle equations work out that your diameter is 14. So when you do it that way, it's 14 and like 1/10 or 2/10. So they round off a tiny bit. But for the most part, you get a bonus tolerance. Well, it's not a bonus tolerance. A bonus tolerance is something else entirely. But you get extra tolerance. You get a circular zone. We'll talk about bonus tolerance in the same topic, actually. So, where was I? This 14 is pretty important. It gave you extra tolerance. Now, what would happen if the engineer in there put 10 thousandths? What would happen is your circle would be smaller. In certain places, it would be smaller than your square, and in certain places, it would be bigger. There's other cases where the engineer might say, no, we need this really tight. We're going to make it 5 thousandths, in which case your circle is pretty much entirely on the inside of that box that you used to have and is no longer anything you need to concern yourself with. So Many applications will choose it this way so that you get a little extra tolerance because, again, going back to our very beginning of the topic, GD&T symbols are meant to represent functional tolerance. When you have diameters, bolts and holes assembling together, or shafts and holes, there's no squares involved. Why is the tolerance zone square? What people a long time ago have realized, well, yeah, if you're a little bit outside of your tolerance zone up here at the top of the box, it's a round part. It's not going to matter. So they give you this style of dimensioning that a traditional plus or minus can't handle. So this is good for you. Most of the time, true position is going to help you. Sometimes it's going to restrict you. So keep that in mind when you look at your numbers. Think about, am I getting extra or am I losing something? So, before we move on, I want to talk about this modifier, especially in context to true position. So I mentioned we would talk about modifiers a little bit. So when you're talking about true position, modifiers come into play a lot. You have something called least material condition and maximum material condition. So it'd be a circular M for maximum and a circular L for least. And essentially, think about a shaft. All right, and we're going to apply a true position tolerance to one of these diameters. Well, what is the least material condition? The least material condition is the smallest diameter shaft, and the maximum material condition is the largest diameter shaft. Now let's think about our angle block and our large through hole, or even our hole that is actually called out as true position. What's the least material condition for a hole? It's the largest hole. And the maximum material condition is the smallest hole. So what engineers do to help with designs is they realize, hey, we've got clearance. So sometimes if diameters are made large but off location, the fact that they're large means whatever shaft needs to go in there will still fit with the clearances we want. So what the engineers will do is they'll say, okay, we'll put a maximum material modifier, and what that will mean is this tolerance applies at the maximum material condition. But if you can get to the least material condition, you'll get a bonus. You'll get extra tolerance. You're going to make a bigger hole, so you get a bigger positional tolerance. So, let's get back to where we were. So when you get that bonus tolerance, this circle grows. And this is mostly applied to shafts that really need to assemble. They'll get that bonus tolerance applied, but it's more often applied to holes because we do a lot more holes that have both assemblies and get a little bonus tolerance or something like that. So you'll see it a lot more on holes. It does complicate things a little bit. You don't necessarily need it, right? You don't need the bonus tolerance if you make the part correct without it. And I'm gonna record a video of a tool that I've created that will calculate the tolerance zone, where you are in relation to it, and how the least and the maximum material condition play out. But that's going to be a much longer topic than I can do in this video right now. So we're going to separate that one out. Just talk about true position. So check that one out if you want more context on true position and bonus tolerance. But that's a quick breakdown of it. Now we're going to briefly talk about concentricity and symmetry. And we're going to start off by saying, if you're going by the latest standard of Y14.5, released in 2018, well, these two symbols have been redacted, made obsolete, no longer in service, however you want to say it. There's an official term, I can't remember. But essentially, from now on, you should be using the position symbol. Concentricity and symmetry were pretty much redundant to position, not only in how you define the design, but also how you inspect it. When you're going to measure a concentricity or a symmetry, you're going to basically measure the position of it. Now, there's one caveat. It's kind of accepted industry standard that over the many decades of GD&T, concentricity has been applied to diameters, and you cannot measure concentricity with one indicator. As I have shown here, this is how you would actually need to measure concentricity. You would need to set up an indicator on both sides of a diameter and measure the TIR difference, basically. And the reason for that comes down to the fundamentals of concentricity definition and runout definition. And the difference is concentricity is a restriction or requirement for the center line of a diameter, and runout is the requirement for the surface of a diameter. And so what people have, what this basically means is there is a difference between the center line and the surface. You can have some very oddly shaped surfaces that are symmetric. Think about something with 3 lobes. Draw it real quick. Oops. We think of concentricity runout really being affected by circles and diameters. So this is the center line, this is the surface. To do a runout check, we'll drop an indicator up here and measure it. But we can't get indicators on a center line. There's no way to do that. So there are some shapes which I will attempt to draw. Assuming I did a very good job symmetrically drawing this, if you tried to do a runout check of this, it would be off center. And if you did a concentricity check, well, this void and this extension pushes maybe the exaggerated center point here, and the exaggerated center point here, and the exaggerated center point here, because this is an odd shaped drawing. But if you try very hard and draw, I am failing miserably. If you try to draw this symmetrically, no matter what distance you take across this direction or across the low points, it's perfectly symmetric. So again, you're going to see a lot of indicator movement on the TIR. It's going to run out like crazy, but assuming this is symmetric, center line is going to be perfect. So that's the difference between a lot of runout error and no concentricity error. This one would have both concentricity and runout error. This one would probably have both as well, depending on the shape. So the reason that the standard pretty much redacted and reduced concentricity, again, you can use position. And I'm also, going to let you know, since a lot of the times it's been applied to diameters and measured with an indicator, well, that's a runout check. So a lot of the checks for the last decades or so that people were doing runout checks to verify concentricity. And that's just how it's been for a very long time, and how engineers have been putting concentricity, and then somebody else goes to measure it with a single indicator, and it's fine. Setting up 2 indicators, that is a lot of work. It requires a special fixture to get them perfectly online, and then you got to move it when you have total, you got to move it to different places. It's really specialized equipment or a lot of effort to do it. And what are you doing? You're measuring the surface with 2 indicators. Well, you might as well just measure the surface with one indicator and do a runout check. They satisfy the same requirement, right? Functional tolerancing. So that's why, when it comes to substitutions, substitute concentricity with a runout check or a position check. Now, if you're looking at a print and it's from an older revision of the standard and it's got these old symbols on them, you're probably going to, most likely you should be checking the symbols using the rules of the old standard. Now maybe your company will have a policy about that and updating prints or updating methods, but you need to have that discussion before you just change what you're doing, because it can have an effect as these symbols change definition over time. There's a reason. They're progressively moving towards more consistency, but each time you change something, it may change what you've done in the past. So hopefully, in the next 10 years or so, you see less and less of them. It makes things easier when there's fewer symbols. And, I'll say, one more thing about concentricity. You can measure concentricity with a CMM. So that's another way people have done it, because a CMM will calculate the center point based off of touching on the surface, but it can actually calculate a center point and how much it deviates along the length of the shaft. So that is another option for you. If you need to verify concentricity directly, the CMM pretty much going to be your only method right now. You're not going to see these double indicators set up and you're trying to, this one's minus 10 thousandths, this one's plus 15 thousandths. So what is that, 25 thousandths at this point? Or what's the difference? It's shifted more to the right than it is to the left. Maybe I even drew that wrong. That maybe doesn't even make any sense for all I know. I've never seen one. I've never used one. I've always set up an indicator and done a total runout check whenever I needed to do a concentricity check. So we're gonna jump into orientation now. So parallelism, perpendicularity, angularity. They're all essentially the same thing. They're all going to give you a tolerance zone that looks like our earlier image from the last video I did right here, where you're going to have, your nominal value, then you're going to have a plus zone that you're not allowed to cross this border, and you're going to have a minus zone where you're not allowed to cross this border. And looking at it, from the side, it would look like this. So they're all basically telling you the same thing. But they all require a datum. So the angle block is a great print for explaining this, because it has all three features on it. Let's look at the parallelism. The first one up here on the right, parallel to B. So if you look through the datum, you'll see that the bottom is datum B. And so what we're looking for is parallel, how flat this is relative to the datum B, which I'm resting on my granite and sort of saying, I haven't really mentioned it. I should have mentioned it maybe earlier. One of the key features of GD&T is to so-called grab the high points, and part of that is because we want to be able to be repeatable, and we want to be able to use these really accurate surface plates and angle blocks. So I did this discussion earlier, and I talked about the 3-2-1 method, and I think I neglected to mention this part of it. So if you weren't understanding that, why we do it this way. What I neglected to mention is, grabbing the high points is the only way to be repeatable, short of a CMM. If we want to do this on a surface plate, the 3-2-1 method on the high points is going to be repeatable. And it's okay to grab the high points and make all of your judgments based on that. As I drew earlier, my kind of jagged little angle block here, this is what we think surfaces look like you know, at the microscopic level, and they may not be perpendicular to each other. They may not be all parallel and square. So we try to grab the high points as we can during the 3-2-1 method. So this helps us with the parallelism check. We're going to put datum B on the bottom and see how flat this is relative to datum B. For this perpendicularity check over here, if you take a look at the full print, it's saying to perpendicular to B, which again is the backside, and we're going to check on an indicator how perpendicular this is. We could use a machinist square as well, which I have on the table over there, but I'm going to do it with the indicator, get an actual reading. And then angularity, we're going to set up a sine bar at 40 degrees, and it's the same thing. We're going to check the tolerance zone at 40 degrees, you know, relative to the datum B. So they're all just, you know, 180 degrees from the datum, 90 degrees from the datum, or a defined angular degree from the datum. So let's just jump into it, since angle block's a pretty good part to work with. So the first thing was parallel to datum B. So that is, let's take a look at that. Parallel to datum B, and my height overall is 2.340. So I'm going to show you a little trick that I usually do to get two birds with one stone. I'm going to measure the parallelism and the size of it at the same time. And we're going to do it with Joe blocks. So I'm going to build up a 2.340 Joe block. So if you remember our Joe block math, we're going to use a 140 and a 0.2. There's 0.2 to get to 0.340. And then we're going to add a 2-inch block underneath that. And we're just, sorry, put it on camera. We're doing our little cross method. Slide it back and forth. And now we're going to do a transfer measurement, like we showed you in the surface plate videos. Many transfer measurements. Looks pretty good. And now this surface relative is already greater by 10 thousandths. So that may or may not be in print. I don't think it's in print. So now we're going to just do the parallelism. We're just going to check, is it moving a lot? It's moving about 1,000th on that side. And it's up to maybe 1,000th and a half at the maximum. So I had 0 over here, or actually plus 10. This is my low. This is my low on my TIR. It's 10. I could re-zero this, right? I told you I'm doing two birds at one stone. So I'm going to say plus 10 is my 0. And then we're going to look for the high point, which was over here, which was about plus 11 and a half. Where was that? I think it was over here. Yeah, right about there. I'm starting to fall off, but so our parallelism, 1.5. So we're passing that, but I was also checking the 2.340. Let's check with a caliper, just because, what do you know, I'm plus 10. So definitely an issue there. Two birds, one stone. Got the sizes wrong, but got the parallelism is right. Next up, we'll do the perpendicularity. And for this, I don't need any Joe blocks or anything else. I'm just going to have to reorient my indicator. And I'm going to be a little bit concerned about cosine error now, because I'm going to be traveling in the up and down direction, so I need to have a good reading that way. And what I'll do is I'll bring this all the way down just above the rock, and then I'm going to bring my part into the indicator. Instead of moving the height gauge, it's easier to move the part, and zero it. Now I'm going to have to apply a little bit of pressure so that this whole part doesn't move as I move the indicator, but now I'm just going to raise my indicator. And what do you know, we're getting a little bit of error. I'm already at 2.5 thousandths, 3 thousandths, and right about there it hits the radius. So about 3.5 thousandths. And if I go back down, I should get back to 0. Back to 0. And I'll check another section of it. So I'll just slide over to another section. This is one instance where I do re-zero because I moved the part off of the indicator and put a new pressure. And so what looked perfectly perfectly perpendicular has about 3 to 3.5 thousandths of perpendicularity error. So, okay, that's cool. Easy way to do it. I'm going to show you the wrong way to do this and why setting up with knowing your datums is really important, and setting up which one on the rock and understanding your call out. So somebody might look at this and say, okay, perpendicular to B within 5 thousandths. And instead of putting datum B on the rock, they're going to put datum C on the rock and run the indicator. So think about what might happen in this instance. Over about 2.5 inches, I had 3 thousandths of perpendicularity error. So what's going to happen when I go over the much larger 4-inch distance? I'm going to do the same check. Oops. All right. I'm going to hold it down, and then we're going to run up. So let's see. I actually don't know what's going to happen. No, we're already to 3.5. We're at 4. We're at 5. And it's just about to fall off. So now we got 5 thousandths of error, just a little bit more than 5 thousandths. So what happened is, the error is being amplified. When you put the larger surface on the rock, it spreads out that surface a little bit more, and you travel a little bit less, so you see less error. And the more you travel, the more error you see. So a lot of people will do that. I've certainly done that in my career. Sometimes you think it's easier to just do it this way physically, but it may not be the best way to do it. Sometimes you can do it this way, and if you're still in print, you're still in print. I won't argue with that, but a lot of times you're going to see larger number than is actually being asked for because of the way the datums are set up. So that's important to know. I think we're gonna take another quick break and continue our video. What's the next topic? I have enough time to do one more check. Let's do this last check. Let's use some new parts. So we have 5 thousandths relative to A. And I'll show you a couple ways you can do this one too. So I've got datum A on the back, right? From the print, datum A is the back surface. And I'll zero this. And I can just spin this around. And another thing I can do is I can just run the indicator, pull it out. Run the indicator, thousandth off. It shouldn't matter whether I reload or unload the indicator. It's possible I bumped the 0 now that I'm looking at it, so there we go. If you're not sure, just double check. But otherwise, maybe a 0.5 thousandths of error. And I think the indicator is getting bumped as maybe a 1,000th of error. Another way you could do this, and this is again the wrong way to do it, but if you flip it over and now you run datum A, lo and behold, you see a little bit more error for the same exact reason with the perpendicularity check. See a little bit more error in that movement. So again, you have more surface. It's resting on a smaller surface, so whatever imperfections are here, it's amplifying because it's on the smaller surface. So just keep that in mind. Try to read the prints, and hopefully the print has been set up in a way that makes sense for the part function so you can verify everything's going to work. So we'll take a break and we'll close up with some rules and some final thoughts. So thank you for watching. Be right back.